Hello everyone. Today we will be talking about the delay of a inverter circuit and subsequently we'll be moving toward the delay of a static random access memory. Today we will be talking about the delay of the inverter only, and in this inverter only circuit we will be talking about the delay of a single inverter, the delay of multiple inverters in series, right? So let us discuss the basic of the delay. Okay, so you see, let us suppose I give this sort of input to an inverter. It is evident and we all know about it that the output of such input wave from an inverter will be like this. But if we slightly zoom this, we will find that this is not as straight as it looks. This actually looks like this way, and the output looks like this way. So what is the delay theoretically? The delay is when if this is 0, this is VDD, this is VDD, this is 0. If this crosses the 50% of the path and crosses the VDD by 2, and from VDD to becoming 0, it crosses VDD by 2. The time gap between these two VDD by 2 is normally taken as delay. This is the signal 1. This is signal 2. The signal 1 is normally treated as input and signal 2 is normally treated as output. I am talking about the things as they happen in cadence virtuoso, right? So by the virtue of this concept, we will be moving towards how the things happen inside the cadence. Now I'm going to take you towards the cadence virtuoso simulator so that you can understand this concept in a better way. Okay, so I am sure that my screen is visible to you all. Okay, so this is the cadence window. In this cadence window, you will see that if you watch here carefully, this is your PMOS, this is your NMOS, this is input, and this is the output. Now we will be talking about how this circuit behaves and how to calculate delay within the circuit. Let me clear all the drawings and come back to the simulator. This is the inverter that we all know how to create it. We'll launch ADL. In this ADL, we will check for the stimuli. Input signal we will be taking as pulse 0 to 0.8 volts. There is no need to write V over here. 20 nanosecond is the period and the pulse width is 10 nanoseconds. Apply. And we are working on the VDD of 0.8 volts only. Okay. So outputs to be plotted, select on design, this output and this output. We will be doing the transient simulation. The first simulation is transient. The stop time, let us say 50 nanoseconds, conservative, apply, okay, you run it. Okay. So what is visible in this? You see this green wave shows the input and red wave shows the output, and they are complementing each other. It means the inverter is running successfully. So once the inverter is running successfully, we will be taking the delay. In the tools, click on the calculator. You will see this sort of window, right? In this window, please note there is signal 1. I'll make you clear the concept of everything which is written. There is signal 1, there is signal 2. Signal 1 is the input signal, the primary signal. So what is our primary signal? Primary signal is the input signal that we have given. We'll click on this. It has picked up the input signal. Now we'll go to signal 2. We'll go to wave shape again. We'll pick you can click anywhere on the wave. There is the output wave. Now what is the threshold value? While telling the concept, I told you that when the pulse reaches VDD by 2, the delay is calculated. So in this case, we have taken the VDD 0.8 volts. So the threshold voltage will be 0.4 for input as well as the output. Now, what is this edge number? Edge number is this is the first edge, this is the second edge, this is the third edge, this is the fourth edge. If you want to calculate the delay between the first edge of input and the fourth edge of output, you can do that. But normally, for the sake of delay, we calculate the delay between these two edges, the similar edges actually. So we will be taking the first edges because the delay is supposed to remain the same. So here we take the edge number 1, edge number 2, right? Now edge type, either. What is the meaning of this? See, this pulse is rising and the input was falling. Means for the first signal, your edge type is falling, and for the second signal, the edge type is rising. But in the next case, the signal 1 is rising, signal 2 is falling. So to avoid this, we take edge type either. It can be rising, it can be falling. Similarly, H2, it can be rising, it can be falling. They can take it to their choice. Click on apply. A formula is created over here. Now let us calculate. It is 36.39 picoseconds. What we'll do, we'll click here so that this formula is shifted to ADL and we'll treat it as delay. Okay. Now, you have seen that we have calculated the delay between the two signals. But what was the point? The point was this output has no load. But if this output is having certain load with it, it will work as a capacitance. Either you add a resistor, PMOS or NMOS, it will work as a capacitor. It will take time for charging and discharging, and definitely your delay will increase because time is 1 by RC, and every transistor will have resistance as well as capacitance. So we'll see once the two inverters are in series, how they behave. So what I'll do, I'll make one more. Okay, so that's how I have done it. So I have taken one more inverter and it's I have given the name to its output. It's out 1, right? And what is the input for this? The output from here works as the input. So now the delay of this out should increase. Now, if I calculate the delay simply by applying the previous method, you please see the delay has increased. Okay. But the thing is like, now we have three signals. Output to be plotted, select on design, out 1. Now we have input, output, out 1. How they look like? Out 1 will be the invert of out. Please see, this is your input, this is your output, and this out 1 is the invert of out. If I can move this to here, like this. Now see, this is input, this is output, and this is out 1, which is the invert of out. And it is very much similar to in, right? Now, what is the delay between this in and this out 1? Let us calculate. We'll go to, in the similar manner, we'll go to give me a second that I can adjust the windows. We'll go to the tools and calculator. Okay. Now for calculator, what will be the signal 1? The signal 1 is I want to calculate the delay between input and out 1. Initially, I calculate between input and out. Now I want to calculate between input and out 1. So if I want to calculate between input and out 1, so the first signal is input here. The second signal is out 1. Rest of the things will remain the same. I'll apply, send it to this. Now this is between in and out 1, right? The first delay was between in and out, right? So we'll calculate the delay now. So this delay is 57.8172, means the delay between input and output out 1 is 57 picoseconds. The delay between input and output is 42 picoseconds. Now, what is the delay between out and out 1? Let us calculate that also. For this case, the signal 1 is out. For this signal, the input is out. We have taken this. What is the signal 2? Signal 2 is out 1. Now we'll apply this, send this to the ADL, and ADL will tell me that that's a between out and out 1. So its input is out. Okay. Now when I run this, you will see the delay is 15.565 picoseconds. Right? Now I give a quiz to you. The quiz is if the delay between input and output is 42 picoseconds, I'll show you here. If the delay between input and output is 42 picoseconds, then why the delay between out and out one is only 15 picoseconds? Considering that these PMOS and NMOS in both cases are of the same configuration. Now, this is a thought for you. Please think over it and write your reply in comments. That's all for the day. Thank you for being with me.